Welcome to the course on differentiable cameras and displays. We are a team of 6 researchers and we have put together amazing content for this course. I am Praneeth and I'm currently a researcher at Princeton University. We have Florian Schiffers, who is a PhD student at Northwestern University, Oliver Cosard, who is a professor at Northwestern University and also a research scientist at Meta. We have Ethan Sung, who is a PhD student at Princeton University, Sungwon Baek, who is a new professor at Post-Tech in South Korea, and Felix Haida, who is a professor at Princeton University and also the CTO of Algolux. To give an overview of the course, I will first present the basics of wave propagation and digital holography. The wave propagation models also come in handy for understanding the rest of the course material. We have also created a nice library called HoloTorch in Python, which has all differentiable wave propagation models. Oliver and Florian will introduce this library, and implementation of the ideas are introduced in the first part of the course. Felix will then talk about the differentiable camera and the idea of making every part of the camera pipeline differentiable for task-specific optimizations. With these ideas, Ethan will talk about reducing the size of cameras to the size of a salt grain using nano-optic meta-lenses. Until this point, you will be familiar with differentiable cameras and displays. So finally, Sungwon will discuss extending these ideas to illumination and temporal sensing and how differentiable wave propagation can be used. So, without further ado, let us jump into the course. Welcome to our course on differentiable cameras and displays. I'm Praneeth Chakravartula and I'm a researcher at Princeton University. In this first part of the course, I'm going to give an overview of wave propagation methods and computer-generated holography. Specifically, I will start off with a brief introduction to waves, propagation, and interference, and then discuss optimization strategies for 2D and true 3D phase-only holograms. Finally, I will introduce you to the idea of hardware-in-the-loop phase retrieval to compensate for real-world errors in hardware displays. So, what is a wave? A wave is nothing but a disturbance that transfers energy from point to point in a medium. As you can see here, a stone when dropped into still water creates a disturbance that propagates through the water, creating a wave. When two such waves are superimposed, their amplitudes might add up or cancel each other depending on how the waves match up. This superposition is called interference. In this example here, you see two identical waves that are created with some spatial separation interfering with each other. Note that the separation will already cause a phase difference between the waves, although their amplitudes are the same. Here, you see the objects being dropped into still water from different heights and at different times. This will create two waves that have different amplitudes and phases interfering with each other. Waves and interference form the fundamental of a holographic display. Before delving deeper into holography, let us first look at how humans view a 3D scene. Multiple angular rays from a given scene reach the eye and get focused on the retina. A light field display, for example, emulates this light transport from the scene by generating angular rays closer to the eye, although in low resolution. Here, I show a top-down view of the same scene. Note that the light field angular rays are nothing but a discretely sampled continuous wavefront. Therefore, you can think of the rays reaching the eye as one complex wavefront traveling from the scene. This wavefront is sampled at the eye and focused on the retina to form the image. In contrast to light field displays, a holographic display directly generates a complex continuous wavefront representing a 3D scene. So, How exactly do holographic displays work? An incoming light wave is typically modulated by a phase pattern, and this modulated wave propagates and creates an image on a holographic display. Computing the appropriate modulation phase pattern is the core challenge of computer-generated holography, and this phase pattern directly affects the quality of holographic images. To compute such phase patterns or phase-only holograms, several heuristic methods were proposed in the past. Gershberg-Saxton is one of the most popular methods. Here, we propagate the waves back and forth between the hologram plane and the image plane and enforce necessary constraints until a good phase pattern is found. This works reasonably well, but is extremely noisy. Another widely used method is the double-phase amplitude coding method, where the waves are propagated to the hologram plane from the image plane, and the complex amplitude is encoded into two phase-only pixels. While this works reasonably well, it is not very robust, and we typically see some loss in resolution and sometimes contrast. These two methods, although widely used in holography, do not result in optimal phase modulating patterns. A logical thing to do is to directly optimize for phase patterns. Let us see how we can do it. You start with an initial phase pattern, propagate the wave, and reconstruct an image. Compute the error between reconstruction and target, and backpropagate the errors into the phase. And you repeat this until convergence. Such optimization should be possible with gradient descent solvers if we can compute the gradients. Although it sounds simple, this approach isn't straightforward, and I'll tell you why. So, as you can see here, we started with a phase-only holographic field. We then propagated the field and take its intensity. We want this intensity to match the target image, so we simply construct an objective function that calculates the error between the reconstructed image and the target image. We can do a first-order gradient descent optimization if we can compute gradients of the objective here. And of course, we can simply apply the chain rule to compute gradients. Here, I want to introduce to you what is called a holomorphic function. Any complex function that is defined on a complex domain and is complex differentiable is called a holomorphic function. And an important property to note is that the derivative of a holomorphic real-valued function is zero. This means the function always needs to be a constant. And if you notice our objective has complex arguments, but its value is a scalar number. That means our objective is real valued, and hence the derivatives of any order are not defined. Without well-defined gradients, we cannot, of course, solve the optimization problem using gradient descent solvers. And this is the reason why most previous methods relied on heuristic schemes. And to overcome this, we look at two important properties of a gradient in the context of optimization. One, the gradient defines the direction of the maximal rate of change. And two, the gradient is zero at stationary points. We then use an approximate gradient definition that follows the above two properties and can be computed using complex Wittinger calculus. And with these Wittinger gradients, you can simply use the standard off-the-shelf optimizers to directly optimize for a phase-only hologram. We published a paper at SIGGRAPH Asia in 2019 on this method, and recently these complex Wittinger gradients have been integrated into popular machine learning libraries as TensorFlow and PyTorch, and so it is easy to implement such gradient descent optimization methods. Here, I show holograms computed using the optimization with Wittinger derivatives. As you can see, this phase optimization results in high-quality holographic images. It eliminates severe noise and ringing present in the previous methods and results in high resolution. You can see the details such as the TV lines are clear in the optimized holograms compared to the others. And here I show color results. The Gershberg-Saxton holograms are extremely noisy, and the heuristically encoded holograms show a loss in resolution and contrast. The direct phase optimization method, on the other hand, produces the best reconstruction quality. Now that we have looked at 2D holograms, let us see how we can compute a 3D hologram. A true 3D hologram projects a three-dimensional point cloud where light is focused on every point using tiny diffractive lenses. Such lenses are all interfered with each other to produce a complex hologram containing both amplitude and phase. And finally, heuristics such as the double phase encoding are often used to convert this complex hologram into a phase-only hologram suitable for today's SLM hardware. However, every step of the 3D hologram computation is inaccurate, which leads to severe artifacts in the holographic projection. To begin with, the target phase of each point in a 3D scene point cloud is typically missing, and therefore a handcrafted target phase is assigned to every object point. The wave interference simulation does not handle the occlusions at depth discontinuities, leading to artifacts. And finally, a phase-only hologram is computed from a complex hologram via suboptimal heuristic encoding methods. All these inaccuracies compound to produce 3D holographic images with severe artifacts. Unfortunately, optimizing for true 3D phase-only holograms is challenging. Before I describe how we can overcome these problems, let us review some common 3D hologram computation methods. There are point-based methods where every point on the 3D model is treated as a point source emitter, and the waves from these point sources are propagated to the SLM to compute the hologram. Layer-based approaches slice the 3D model into several planes and propagate waves from each plane to the SLM. But this does not support continuous focus. The most successful approaches so far have used light fields to encode depth and view-dependent effects. However, these methods have poor spatial and angular resolution due to their dependence on Hogels for modeling the light field. One most important thing to notice here is that all of these methods compute the complex wave field at the SLM, followed by some heuristic encoding, like the double phase encoding method, as high quality optimization of true 3D holograms has not been possible so far. We proposed a 3D hologram optimization method that lifts these limitations and enables phase-only optimization of 3D holograms for the first time. I will next review 3D scene representations suitable for true 3D holograms. Today, the most common 3D scene representation used in holography is an RGBD image. The yellow boundary here represents the depth data. Each visible point in the scene is assumed to be a spherical point light emitter, and holograms are computed using point-based methods. Note that the rays around depth discontinuities are occluded. While such an RGBD image provides enough light transport information for visible scene points, it cannot provide parallax cues due to missing rays at the occlusion boundaries. These missing rays also cause inaccurate wavefronts between the foreground and background objects. Another popular 3D scene representation method is multiplane images, where a 3D scene is sliced into multiple depth-based image layers. This way of representing the scene provides huge computational advantages for generating a hologram compared to point-based methods. Unfortunately, this also suffers from similar errors at occlusion boundaries. Moreover, to achieve perceptually correct focus cues, we require extremely dense sampling of the depth. In contrast to these scene representations, if we use a 4D light field, all depth cues and parallax information can be encoded in its different angular views. Note that a light field is nothing but a coarsely sampled wavefront. Therefore, propagating the underlying complex wavefront and sampling it generates a light field angular view. If we are able to recover the complex wavefront from the coarsely sampled light field wavefront, we will be able to represent a true 3D hologram with continuous focus and parallax cues. We formulate this wavefront inversion as an optimization problem where a full complex wavefront is sampled and the reconstructed images are matched to a target light field. Unfortunately, since the optimization objective is a sum of penalty functions for every single light field view, the computation required for solving this problem scales directly with the number of light field views. So we reformulate the problem and invert the light field into a sampled approximate continuous wavefront. To this end, we invert the light field scene into a wavefront using a wavefront inversion operator and try to optimize for a continuous wavefront that can closely resemble the inverted wavefront. Finally, in order to compute a phase-only 3D hologram, we further relax the constraints of the problem and solve it as a continuous volume optimization problem. Here, we match the wavefronts inverted by the light field over an arbitrary continuous volume with wavefronts modulated by a phase-only SLM. Note that the phase of a given wavefront manifests as the amplitude over a continuous volume. Therefore, matching the wave evolution over a continuous volume is equivalent to solving for a complex wavefront. Solving this optimization problem produces high-quality true 3D holograms with continuous focus and parallax cues that are encoded in a light field. And note that the optimized wavefront also synthesizes continuous views that are originally not present in the input light field. Here, we show a time-lapse of our 3D hologram optimization across a continuous volume. What you see here are arbitrarily chosen focal depths across the scene volume. Starting with a completely random phase, the optimizer finds a phase-only hologram in about 500 iterations. The resulting optimized holograms eliminate perceptually apparent artifacts that are present in the previous state-of-the-art methods. You can see how our method also reduces the light leaking across the grass blades and ringing artifacts and produces high-fidelity reconstructions. In this far-focused image, the white branch in the background is in focus and the grass blades in the foreground are out of focus in Hogel-free holograms. Whereas the previous state-of-the-art tensor holography produces inaccurate focus cues and extreme artifacts around the grass blades as well as the background trees. We display the optimized holograms on the hardware you see in the top right. Here, we compare our method with state-of-the-art light field-based stereogram approaches. As compared to the phase-added stereogram and overlap-added stereogram approaches, you can observe significantly reduced aberrations at both near and far focus for our optimized Hogel-free holograms. And the details in the trees and leaves correctly demonstrate defocus blur when changing the focus point. And here is another scene. It can be clearly observed that our proposed technique reduces aberrations and produces correct defocus effects at the tree and the cattails near the pond. Here, I show the parallax cues of the holograms as captured on a hardware display prototype. To summarize, we discussed that existing holographic methods do not support parallax skews and only compute phase heuristically. On the right, you see a 3D hologram reconstruction by today's state-of-the-art method. Missing parallax skews and heuristic phase-only computation result in inaccurate focus skews and light leakage at occlusion boundaries and depth discontinuities. In our work that's shown on the left, we directly optimize for the 3D hologram phase and get rid of the severe artifacts to produce high-fidelity true 3D holograms with accurate focus and parallax at depth discontinuities. While both the 2D and 3D hologram optimization approaches work the best in simulation, unfortunately, the quality of images on a real display is not at par with the simulations. Let us look at why this is the case. Basically, the problem is that all these approaches implicitly also make simplifying assumptions of the display, such as perfect collimation, continuous SLMs, and perfect lenses, which would produce a clean image on the display similar to our simulated reconstructions. In other words, if the real holographic display was ideal, a hologram computed using the existing ideal wave propagation would result in similar superior quality images. However, a real display has several non-idealities, such as non-uniform illumination, imperfect lenses with scratches, pixelated SLMs with nonlinear phase modulation, and aberrations in lenses, and so on. And all these deviations combined makes the images coming out of the hardware very noisy, resulting in poor image quality. As a result, when shown on a real display, these holograms show severe artifacts because of the underlying non-ideal real-world wave propagation, which is both unknown and severely deviates from the ideal wave propagation. Since the wave propagation model is unknown within a real holographic display, one way to compensate for the real-world aberrations is to optimize for images coming directly out of the display. For this, instead of simulating the reconstructions, we can directly use the images as captured by the camera in the optimization. This approach can eliminate many artifacts, but unfortunately, this is slow and impractical, especially for display applications. Moreover, having a high-resolution camera that sees the images exactly as seen by the eyes increases the bulk of near-eye displays undesirably. One way of overcoming this is to calibrate for all the real-world deviations and use this calibrated model to generate holograms. Although it doesn't work as well as having an active camera in the loop, it can suppress many real-world artifacts. But unfortunately, this method requires identifying and calibrating every individual source of error. It is challenging to calibrate for all the sources of error, and this approach is fundamentally limited by the calibratable parameters. So to overcome all of these limitations, we propose to learn the entire real-world wave propagation in a holographic display using a deep neural network. Once the network is trained, we can simply replace the real hardware with differentiable learned hardware and use it for holographic phase retrieval. Here, I compare images produced by different state-of-the-art hologram computation methods. Here I show double-phase holograms, Whittinger holograms, and our method. In this example, if you observe the background, you can notice how the black regions are truly black. Achieving good black levels and high contrast is one of the major challenges of a holographic display. And this learned hardware in the loop method achieves unprecedented contrast and state-of-the-art image quality. This is another live captured video from our holographic display. Observe how the fine feathers on the peacock are clearly revealed and the improvement in overall contrast of the image. With this, I end the first part of the course. To review, we started with a brief introduction to waves, propagation, and interference, and discussed optimization strategies for 2D and true 3D phase holograms. Finally, we looked at learned hardware-in-the-loop phase retrieval to compensate for real-world errors in hardware displays. The next part of the course will go deeper into these ideas and show implementations of various phase retrieval methods. We have created a nice library in Python for experimenting with various holographic methods that also includes Whittinger gradient descent optimizations, and we hope you find it useful as well.
Hello, and welcome to the tutorial on HoloTorch, a differentiable coherent light transport software package written in PyTorch. So my name is Ollie Kosart. I'm an associate professor at Northwestern University, where I run the computational photography lab for the last decade or so. And I'm also a currently visiting researcher at Meta Reality Labs, where my student Florian Schiffers and I have built HoloTorch during our time working together there. Now, HoloTorch was developed not just by the two of us, but also by a number of other colleagues, including the researchers you see listed here, for both Reality Labs and the Princeton Research Group of Professor Felix Heide. All of our source code is open source, and you can find it on the GitHub link here, or by scanning the QR code on the product left. Now, I've been working on holography research on and off for almost 3 decades, and I'm very excited by this new wave of applying differential models to holographic display research that we'll introduce in this tutorial. I actually first started working in holography almost 3 decades ago as a teenager, assisting holographic artists. And holography was originally an analog medium. The first holograms that were recorded were hard copies. They were recorded on film, just like old photographs. And it wasn't until relatively recently that the medium transitioned to a digital format. In particular, dynamic holographic display using spatial light modulators has only been around a few decades. And the tools for performing efficient numerical optimization of these type of computer-generated holographic displays is really just emerging, which is really what motivated us to build HoloTorch. So in this tutorial, we're going to step away from using differentiable image formation models for image sensing and restoration and focus instead on image synthesis. In particular, we're going to focus on the specific problem of holographic display optimization using HoloTorch. And at its core, HoloTorch provides a very easy to customize optimization toolkit for holographic display systems research based on automatic differentiation. It allows you to implement a coherent optics simulation very quickly and efficiently without having to reinvent the wheel each time. Now, why would you want to use HoloTorch instead of another open source holographic display codebase? Well, firstly, HoloTorch provides all the basic functionality for holographic display simulation and optimization together in one unified package. It provides parameter specification, modular forward model formation with a variety of optical components like lenses, spatial light modulators, free space propagation, and holographic optical elements. In addition, it streamlines dataset creation, optimization, and visualization. So we hope HoloTorch will pave a path towards a common code base for holographic image optimization and display calibration. We wanted to provide an easy entry point for new researchers to start exploring holography research, and also provide all the necessary functionality for more advanced researchers to quickly prototype new ideas using more complicated optical models or optimization procedures without having to re-implement everything from scratch each time. We've taken care of a lot of things for you under the hood, and we have a number of additional features we intend to add soon, like hardware control for cameras and spatial light modulators for camera in the loop optimization, and more advanced optical sources like SLEDs and LEDs. As you'll see in this tutorial, HoloTorch is designed to be modular for fast prototyping of new and more complicated optical models. All of our models that we've implemented, like ASM kernels and Fourier transform lenses, are implemented in an abstract way, so you can reuse them and assemble new models quickly. This basic HoloTorch functionality is currently documented as a click-through example in the Jupyter notebook that Florian Schiffers will explain in detail in the remainder of this talk. First, Florian will walk you through how to simulate a double phase encoding hologram, then move on to how to solve a phase retrieval problem for near-eye display, for near-eye and Fourier transform holography setups. Finally, we'll discuss two recent algorithms called Aton-D expansion and neural Aton-D expansion. And now I'll pass the torch to Florian, and he's going to start with the basics of HoloTorch functionality.
Hello, my name is Florian Schiffers, a PhD student at Northwestern University, which by this Oliver Coherent, and together we have built HoloTorch during our time at Meta Reality Labs. I think HoloTorch can provide a tool for really fast prototyping of new complicated optical models without having to re-implement everything from scratch. All of that is currently documented in Click-through example notebook that we provide here. So with that, I want to start, and we're going to talk first about the basics of HoloTorch. So you would start by importing HoloTorch, and then from HoloTorch you can import units and just use them like 10 millimeters, 1 nanometer. And the first and most important component of HoloTorch is the electric field module. So the intention there is that we're modeling an electric field, which is spatial extension, and inside of this field we can have complex values. Electric fields are 6-dimensional objects. They have the edge dimension, the time dimension for time multiplexing, a pupil dimension, for example, which can be used for light fields. We have a channel dimension for wavelengths, and for example, for partial coherence holography, or if you do RGB imaging, and then of course the height and the width dimensions. They are always the same, and every tensor will be cast as a 6-dimensional object that is just for type safety, and it makes things easier to implement. So you would import that, and then, for example, we're going to create here a small object. First, we're going to start by initializing the tensor. It would be a tensor by 1000 by 1000. It's 6-dimensional, and we're going to make it complex, so we add like 0j. Then we're going to set the center of it to 1s, and then we can put this data that we just created into our electric field, give it wavelengths of 532 nanometers and spacing. So you can see with the spacing here that we have a wavelength. This is going to be useful because our optical models, when we implement them, they know of the spacing and of the wavelength, and they're going to react dependent on what kind of field they're going to be passed into. You can visualize the objects, as you can see here. See this white object. Well, you can notice that because spacing is a Bender variable of these objects, that the lateral coordinate system here for visualization is adapted. So we see that in real units and not in pixel units. And this will adapt anywhere in the optical path, so we always get real units out. Sometimes plotting can take a lot of time, so we have this rescaling operator inside of our electric fields. For example, you want to rescale by a factor of 0.25. You can see that the spacing will automatically adapt. So instead of 8 micrometers, if you have now 32 micrometers, because the pixel gets 4 times larger. And you can see here everything is downsampled. And if we visualize this now, we can see that we have exactly the same image. It's just downsampled, but the spacing remains the same. Next, I want to start with propagators. So we'll discuss here the angular spectrum method propagator. It's basically this convolution integral. So we're going to discuss now how it can be used in HoloTorch. First, what you have to do is you would have import the ASM propagator. You define a distance. We set it here to 50 millimeters, and then you can put the electric field that we've just created through our forward method. So you can visualize this field, and you can see here on the left the input field as we've defined it, and the output field, you see a propagated field with the typical coherent 3D effects. You can also visualize the ASM kernel. So these are methods which are implemented in the ASM propagator object. So our different objects or different optical components that we've implemented in HoloTorch, they all have specific member variables which make it easier to debug, to visualize, etc. So if you can visualize this kernel here, we're going to see here it has a uniform amplitude, and you can see that the phase here is typical for with an ASM propagator. We also take automatic, for example, count of large propagation distances. For example, if you choose 250 millimeters, we can now see here that we would get aliasing around the larger frequencies because our spatial frequency grid cannot support these large frequencies anymore. And so we basically put them to 0. You can see here, for example, the amplitude is no longer 1s, but zeros actually, where this frequency can no longer be supported. Next, I would like to build a simple 4F system with HoloTorch. So 4F system consists of 2 lenses. The first is a 2F system with the identical focal length. And then the second lens, which can be the same focal length, could also be another. And then we have magnification given by the 2 focal lengths. And in here is the Fourier transform, because the 2F system is a Fourier transform. So how do we implement it in HoloTorch? First, we would import the Fourier transform lens. Then we can define the focal lengths. And we're going to choose here 1500 millimeters. You're going to define again an electrical field. Just in this case, we're going to make it smaller. You're going to make it a smaller image. So you can visualize that again. We're going to put the same wavelength and spacing, and then you visualize, we see now here, this is basically a small rectangle. Now we can pass this through our lenses. So we just call lens 1 and we put the field input. It's going to we're going to enter with the Fourier plane, and then we have the second lens, and you're going to put our Fourier plane image to the second lens, and then put in the filtered image in Fourier plane. We can look at the spacing at the various planes. So we're going to look at like the input plane, the Fourier plane, and the 4F plane. Because like we propagate the spacing at 8 micrometers, at the 4F plane 3.25 micrometer, which is going to be defined by the focal length. And so the spacing at the 4F plane is 60 millimeter. That's because we have chosen here like the second focal length to be 100 millimeter. This is twice the first focal length. So we can see here the correct magnification factors. You can also then visualize the 4F system. You can see here in Fourier plane that you can see the Fourier transform of the input image, and then the Fourier transform of the Fourier plane. And we see here, because the spacing has changed, there's a magnification, and then the real units here go from -8 to 8 millimeters instead of -4 to 4 millimeters. So that's something you don't have to take here in HoloTorch, because this is done automatically for you. Instead of building something like that, you can use our built-in 4F system. So you just have to import it from optical components, and you want to define the aperture radius in addition to the two focal lengths. We'll choose 0.25 millimeters here. And now we're going to introduce you to our first dataset classes. Here, this is the single image dataset, which does the reading and processing of the images for you. So we have here prepared an example image called Tiger from Diff2K, which is like a large image, obviously in GB colors. But we can define here in a single image dataset what the number of pixels in X and Y direction should be, and if it should be a grayscale image. So this will spit out a 5-dimensional tensor because it's not yet batched. That's how datasets in PyTorch work. And then we can access this data. It's going to be 5-dimensional. We're going to extend it here to 60, and then we pass it into our electric field component. And again, we can visualize that. So we're going to see here now this Tiger image. We will now pass this Tiger image through our 4F system. So in our 4S system, we just redefine it here, put the 0.15 millimeter large aperture in here. We can just pass our field in, and before we look at the output of that, first we want to let's look at the aperture. So we look at the 4F system has a member variable, member object, which is like the aperture itself. And the aperture, again, because this is not a PyTorch tensor, but it is an object, you have again visualization methods. For example, on the left we see the amplitude, and on the right we see the phase. Our aperture is like 0 in phase, and it's a very small aperture. So there's nothing very special happening here right now. Again, we can verify that the spacing is correct. We still have a magnification factor of 2, so the spacing is good. And we can look at the output of our 4S system. We see here that this Tiger is like low pass filtered. It's coherent. We can also see that this image is flipped because we have 2 Fourier transforms in consecutive order. And in the real 4F system in a physical setup, we would also see this flip. The next example is using double phase amplitude encoding for phase-only holography. For those who don't know, double phase encoding or DPAC is like a very standard method, which allows you to display complex fields on a phase-only SLM. So first, again, you're going to use our single image dataset to load the Tiger image. But note here that we have like a different number of pixels in X and Y direction. This is going to be important later when we look at the aperture. So here again, we see the Tiger image in larger resolution, and now we will use from our optical component module library, we're going to import DPAC. DPAC is basically a class which does the encoding for you. And then we can call the DPAC generator method called compute DPAC phase. So we're going to input the electrical field, has a 0 phase currently, and then we're going to say that the max phase of our SLM should be 2 times pi. So there's different SLMs, so that's why there could be like different max phase. I think in typical our SLM supports 2 pi because it's the easiest to put on. We then will compute the electrical field. Again, the phase modulation is going to be a 5-dimensional output. That's because by default an SLM doesn't support the pupil dimension because it's in general something which for us happens after the SLM. And now we can see here the SLM has exactly the same resolution as the input field, and then we can create this electric field which is encoded with the double phase encoding method. If you want to know about how double phase encoding works, you can feel free to go inside of the code and you can see the implementation of it there. If you look at the visualization of double phase encoding, so basically what happens is like that each pixel or neighboring pixels, they're going to be encoded with basically a pi minus pi offset. There's a little bit more complicated in the way we've implemented with Argos-Kosner's way. Basically see here, this target pattern is encoded and there's just a checkerboard pattern that you can see. So again, we have a 4F system, but in this time we're going to have like this flag flip. Set to true, that means that we're going to flip the Fourier transform so that we see something upside down. And then we can send this to our 4F system, and we can, for example, visualize the aperture. So the aperture here is going to be non-square. That is because like we have a non-square or rectangle field of view. And if you perform a Fourier transform, you're going to have a different spacing in an XY direction. And that needs to be taken care of. And that's like what HoloTorch is doing for you. So if you want to look what's happening inside of this path, that doesn't mean that they can like go inside of the actual optical path and like propagate to anywhere. What I mean by that is like, for example, you want to see what's happening to your electrical field right after the first Fourier transform lens or after you apply the aperture, etc. That's sometimes useful for like debugging. For that, you use the add output hook function, which is implemented for every component. So you basically access the aperture or the lens from the 4F system as a member variable, and then there's this function add output hook. So we do that, and then we just have to call the model again, and then the electrical fields after the Fourier plane and after the aperture are saved here. What we then do is we also going to first clear the outputs and delete the handles. So this output hook, that's because we do not want to save the output every time we call this method. So these are just some cleanup methods. And like once we have done this, we can now look at the outputs that we had saved here. So this is the object Fourier plane and Fourier plane after apertures. These are electric field components. So we can look at the shape, nothing spectacular here, and we can visualize them. So on the left here, we see just a Fourier transform of our debug encoded field. And we can see at the top in the corners, we basically see the replicas of the higher order terms of the DPAC. So these were created by the checkerboard. And then here on the right, you can see the filter, which basically crops out these higher order terms and leaves us only the desired electric field back. And finally, I want to talk about this misrepresentation of the apertures. I already talked about that, like the spacing in X and Y direction is different because we had a non-square input fields of view. You can see here the units are actually correct. So we go from -3 to 3 millimeters in both directions. However, it still looks like an ellipse. And if you don't want to see an ellipse because you find it confusing, if you're debugging, you can just put in this adjust aspect equals true flag here, and it will basically put them in the same coordinate system. So you see the disk aperture actually as disk aperture. Finally, we can look at the DPAC results. Can we put our field, our DPAC encoded field, to this 4F system? And when we visualize that, we can now see here on the right, that is the output that was created here, field out. We can see that's the perfect image of our tiger. And on the left, we just see the DPAC field, which was like downsampled, just so you can convince yourself that the input was actually something that's way more complex than just like the right image. Like there was no magic going on. So far, we haven't seen any more complicated algorithms. There was no algorithms really involved so far, I would say. Next thing, we want to build a simple phase retrieving algorithm. So basically, the problem is here that we have phase only SLM, and then we have some near field propagation modeled by an ASM or angular spectrum method kernel, and then we have a detector which detects the intensity from the electric field by the square operation. So the problem here is that we have we have no idea what the SLM should look like, basically a random field, and like the forward operator here would give out a random field too. And the idea is then that we solve a minimization problem, typically written down as an L2 or MSE optimization problem. We use gradient descent to optimize for the SLM pattern so that it gives us a good image out. So we do this by first defining the full optical path. And in HoloTorch, we normally define the optical path from the very beginning. That means from the source to the SLM, to the propagator, to the detector. And each of those is an individual component. So we start by defining our source. And this is now a little bit more complicated, but it has a lot of reason because the HoloTorch is used for more complicated algorithms. For example, for partial coherence holography. And there you have to keep track of dimensions, spacing, different wavelengths, etc. This is basically, in those toy example, this should maybe like give you an idea how this could be used for more complex algorithms. So we start out with defining a source. We give it a height and a width spacing, and we're going to use 3 wavelengths or RGB. We can create a source and look at the output of the source. We can see here it's a 6-dimensional object, an electric field, and it has like 3 different channels for RGB, and the height and width is the same. Next would be that we initialize the SLM object. Basically, an SLM is like an abstract object which a field incomes and outputs a field and it interacts with this field. And this is SLM phase only. There's different implementation of the SLM that we've implemented with this one. Basically, just changes the phase at each pixel. We have to define height and width, the number of channels, the feature size of this SLM. We're going to give it like a random initialization. It means like the phase values of this SLM are initialized by random. And the variance of the pixels, they're going to vary like slowly with like variance of 0.1 pi. So when we create this model, you can see here, this spits out a 5-dimensional object. The first one stands for the wedge, the second one stands for time, third one for channel, and then height and width. The lens by default, if you omit the pupil dimension. So the output of that is the tensor or the parameter which is stored in the SLM is actually not an electric field, it's just like a 5-dimensional tensor. Then again, you can visualize that because these are objects, and you can see here that your 3 different wavelengths, they're initialized random. Next, we're going to create the propagator. We're going to use the same ASM propagator we've looked at before, 50 millimeters, and then we're going to define a detector. Here, we're going to say it's a time multiplexed detector, so that we have like RGB in sequential order. And we can again give it the height and the width dimensions. We could like do something different. The detector is actually a more complicated object. It would integrate over all of the wavelengths for partial coherence, holography, if you do time multiplexing, or you have a biofilter, or if you have like time multiplexed holography, for example, which is used for binary CG. And also it can downsample. For example, you would choose like source height over 2. It would actually have a ning operation or a linear operation if you want upsample in the end. So like all things that you don't have to take care of when you do that. So then we have all of the components, so we can initialize or assemble the complete model. So like any HoloTorch model is actually a class. And we should look at this example here, which we call near field hologram. So this extends from the space setup class, which has some basic functionality, which I don't want to talk about right now. But essentially, we're going to define the constructor. So we're going to give the 4 components. Then we're going to call it the super method, of which we're going to call like the constructor of the base setup method, and we're going to put these 4 methods as member variables. And then the only thing which is left is that we have defined the forward operator of our near field hologram, and this is very simple. So first we're going to have the source, which creates basically for now a field of ones. So that we can put this electric field through the SLM, then through the propagator to the detector, and that's returning intensity. And then the output of that forward is now an intensity field and no longer an electric field. So now we've defined the class, and the next thing is that we create the model. So we're going to put these 4 things in. That's an our hologram model. We can print, for example, the parameters. You can see here there's the data tensor. That's the SLM tensor. This 5-dimensional object that I've talked about before. And then we also have a scale variable, and that's because for phase-only optimization and gradient descent, it's more robust if you put a scale into the optimization approach, which makes your optimization a little bit more robust. This basically takes care that the intensities map well with the target that you're optimizing for. We can look at the state dict. The state dict is everything which is going to be moved onto the CUDA when you call CUDA. So you've seen here, I've called like this CUDA method, and the whole model was now shifted onto CUDA. And there's like different components in there, but this is basically this is important for PyTorch Lightning when you do multi-GPU support. But I just wanted to mention that like you can look at this and then you can debug if sometimes the code is not working. For example, if like a tensor is not moved from like CPU to the corresponding GPU. If you look at the forward method of our model, we can now visualize that, and of course, because like we have like randomization, we get like only the random output out. And that is like where now the optimization approach actually comes into play. The first thing is that we have to create a so-called torch data module. Data modules are a specific instant which is required for PyTorch Lightning. And they're similar to torch data loaders. In fact, like there's torch data loaders as member variables inside of the Holo data module. So we're going to start with, again, taking the single image data set with our tiger image. We're going to take the input and output our detector, which is a tiger image, which is colored. Note here that we've called like this Holo data module, which is a method, this PyTorch Lightning method that we've implemented. All you have to pass it is the data set. This can become a little bit more complicated, but then we don't have to worry about this now. So we see this colored image, and we can see for this data set, when we call this data module, that this image is for now on the CPU. But if you want to like preload this on the GPU, and you might want to do this because it's more efficient, like everything is already in your GPU, so you don't have this transfer times between CPU and GPU. You can preload this object onto the GPU, and now if you call this bench, you can see here it's on the graphic card instead of like in RAM memory. And this particular works also for like larger data sets. Of course, it's again only toy example. The next step is that we have to create the Lightning object. So Lightning modules is the way how you implement your optimization routines. So you don't have to implement gradient descent by yourself, but it basically helps you a little bit to streamline optimization approaches. And so we've implemented this SLM Lightning, which is essentially a gradient descent or an atom optimizer, which have like different functionalities, especially like for logging, like logging losses, etc. So we're going to create this Lightning module. All you have to do is you have to input the setup. That was the hologram model that we created, the data module, and the learning rate for the SLM. So the next thing that's maybe a little bit special, it's a PyTorch Lightning thing. It's a trainer, and the trainer basically takes care of like how exactly you want to loop through like the whole data set, and has like stuff like a logger, profiler, like how many GPUs you want to use, progress bars, summaries, etc. The only thing, you're going to define the maximum epochs to be like 200. And then what we're going to do is we're going to pull the fit method of this trainer. So you're going to put in like, what is the model that we're going to train with? It's the SLM Lightning that we've created here. And then we're going to also give it the data module, and we're going to train it with the data module of our SLM Lightning module. So this will now run through about 200 iterations. It is fairly quick because it's implemented on a GPU. So this will be finished in about 5 seconds. And once this is done, we can look at the loss. So we can see here the left the MSE loss, which is decreased, and we can look at the PSNR loss, which is freezing. So basically we will have like a perfect reconstruction of our image, which you can verify by like holding the forward of our method. It's going to give us the output. And we see we get a perfect tiger image here. And of course, we can also look at the 3 different patterns that were generated. You can see for each wavelength, we have a slightly different SLM pattern, because the ASM kernels, it depends on the wavelength. So I would expect that you would have like not first like a different pattern, even if like it would be grayscale, but also because like each channel in this image looks different. So that is why we see 3 different images here. In this session, we talk about how you can implement heterogeneity expansion in HoloTorch. Heterogeneity expansion, originally proposed by Grace from Meta Reality Labs, is a method that deals with the limited heterogeneity of a digital hologram. Heterogeneity is defined as the trade-off between the eyebox and the field of view, and is limited by the pixel pitch of this SLM. In heterogeneity expansion, one puts a scattering element directly after the SLM, and then the light coming out from the SLM is getting scattered, like the field of view is getting expanded, and essentially you get an expanded heterogeneity setup. However, by introducing a random scattering element, you introduce randomness. It means the image that we're going to display cannot be displayed without any reconstruction method. You cannot just use double phase encoding. You need an image reconstruction algorithm to get the image. We do this by defining a forward model. The forward model is very simple. It's just the SLM pointwise multiplied with the hologram. The SLM has to go to an upsampling operator, and then we compute the Fourier transform of that, and then the intensity operator. This whole thing is put into a minimization problem. And note here in this minimization problem that there's an incoherent filter. That means it works on the intensities, and that's basically just like a low pass filter. So let's start building this. So first we're going to implement or import the expansion setup. We've pre-implemented for you. And now instead of creating our components the way we've done it before, by like first creating the source and then the SLM and then the detector, we're going to now define basically configuration lists. So we're going to have like you can think of it like having a large files, which define how your model should look like. And then from this configuration list, we're going to create the actual model. For that, we have these parameter component classes. The first class are going to be model arguments. So we're going to say that like we have 512 pixels in X and Y as dimension, and a spacing of 8 micrometers. We have an expansion factor of 4. It means we're going to upsample each pixel by a factor of 4 in each direction. So we're going to go from 512 to 2000 by 2000 and 532 nanometer wavelength. And then we can define the source. The source is like this parameter source list, and we have like the height, the width, spacing, wavelengths, etc. Just to show you like how we can create a source from that, we have these factory methods that I've already imported, and it just call a create source on like this on this dictionary basically, and then you create a source and it returns a 6-dimensional field, electric field that you've already seen before. And we do it in this very much the same for the SLM. So we define pixel spacing and resolution. We say it's a phase only SLM with the random initialization. We create the SLM so that it works all perfectly. Then we have the expander. It's a new element. We first define the number of pixels of the expander. So we're going to have 4 times the number of pixels. So they have 4 times because it's the expansion factor. And the spacing is going to be 4 times smaller. We're going to initialize the expander as a phase only hologram with random initialization. And the random initialization is going so that it's initialized between 0 and 2 pi. And yeah, so that's why we need the center wavelength so that we can make the correct initialization. Because this is actually a material, it depends on the dispersion coefficient, and in order to find the correct initialization, we need to put in the correct wavelength for the responding material. Then we have a propagator. The propagator is a Fourier transform propagator. We can create that, of course, it works like we've seen that in the 4F system. And then we have the detector. And the thing that should be noted here is that we take in the number of pixels of the model as it was 512. That means like after we've been upsampling at the SLM, we're now downsampling again, and this corresponds basically to this perceptual filter that I've mentioned earlier. The next thing is that we're going to create our expansion setup. So we've imported it already, and now we pass in these parameter components like the source, SLM, expander, propagator, and detector. These are not yet created. They're going to be created in the constructor method of the expansion setup. So this is used, for example, when you do parameter sweeps. So you can basically define your config files, and then you can like create the actual components in the constructor method of the specific setup. And now you can basically look at the forward method, and you're going to see it's going to be like all random because like we've initialized everything with random. Next thing is that we're going to have, again, a data set. We're going to use a single image data set, and we're going to create the data module, so nothing new, exciting happening here. We can reuse now the SLM lightning module. That's exactly the same that we use for the face retrieval. And we can use that because we only have to optimize for the SLM. So it's still gradient descent. Nothing else changes. The train is going to be the same, except that we're just going to optimize for 100 epochs, and then we can run this optimization. It's going to be 100 epochs, going to be again fastest on the GPU. And we can visualize the loss, and we can see here this loss increases, but it saturates around here 22 dB. If you look at the forward model here, and we can visualize that, and so we have taken here to look at the forward and created the intensity field, which is output, and look at the target to, and here's the difference. And we can see that the expanded heterodyne is a little bit noisy. And that is a property of simple heterodyne expansion, that like while we can optimize for something, heterodyne expansion comes at a loss of contrast. So here we show how we can implement neural heterodyne expansion in HoloTorch. It's a paper which was proposed by Beck et al. From the Princeton group in cooperation with Meta Reality Labs. And the idea here is that instead of using a random diffuser, you're optimizing for a so-called neural heterodyne expander given a large data set of images. The cost function stays very much the same, but now we optimize for k different images. So we have to optimize for k different SLM patterns. And at the same time, we optimize for one static hologram H. Let's see how we can implement this in HoloTorch. First, we have to use a data set. We're going to use diff2k. We're going to download a chain data set of 100 images. I've already done that for you. And now we have to define our Holo data module. And now this is the first time that we're going to have like more than one image. We're going to use a batch size of 5. We're going to use 15 images in total. We're going to use it because we're going to have like a faster optimization, but we can principally go to like 1,000 or 2,000 images. Now when we can generate this data model, we can see we have 3 batches with 5 images per batch each. We can preload this data module to our GPU, and then we can visualize that by calling the visualize grid method of the electric field component, intensity field components, and we can look at the images of the different batches here. So there's like this num row and num column so that you can look at more complicated figures. Or you can more complicated visualization methods. Next, we have to initialize the structured light modulator. The SLM is no more complicated because we have to dynamically save and load the phase patterns during optimization. But like if you have like 1,000 or 2,000 different phase patterns, you cannot store this in the GPU anymore. So we have to like fetch this dynamically from RAM or from hard disk. But that's all done under the hood in this SLM class. And you can see this when you create this, that we indeed have like 3 batches with 5 images per batch each. It matches the Holo data module. Next, we will assemble the expansion setup. So we put in our parameter list as we've done it before. And if we look at the parameters now, we can see we optimize for the SLM patterns, 5 images per batch, and we optimize for the thickness of our expander. Then you're going to create the neural expander lightning object, which we've implemented for you. And the only thing that we have to change is we have to change the learning rate of the expander and the learning rate of the SLM. We also set the number of pre-initialization steps. That means that we're going to overfit for the SLM patterns before we start optimizing for the hologram itself. We're going to create a trainer object with 100 epochs, and then we run the optimization. Now the optimization finished, we can see we have first pre-initialized with fitting, and then we have run the neural optimization where we optimize for both the SLM patterns and the expander at the same time. You can visualize the loss. You can see here in the beginning, we have like the saturated loss of just heterodyne expansion. And the moment we turn on neural heterodyne expansion, the loss really starts to increase. You can look at the forward model, and we can see indeed the images that we have now optimized for, they are noise-free. In the interest of time, I have just run heterodyne expansion again with like this speech set, and we can see here the comparison between neural expansion and simple expansion. I've also zoomed into here so we can see that in the cropped version, we can indeed verify that neural expansion works much better than simple expansions. There is a little bit more in this Jupyter notebook, so feel free to look at that. In particular, I talk about saving and loading of models. But if you like that, feel free to download HoloTorch. And Ollie and I will always available for questions. Thank you so much.
So in this next part of the course, I will present what I call the differentiable camera. So cameras have really become ubiquitous interfaces between the real world and computers. We have cameras in our personal devices, in our smartphones, cell phones. We use them for diagnostic purposes, in health applications. They're essential for navigation in robots. We use them in AR and VR applications, and in our self-driving cars. Such as the camera that I'm looking at now here, a camera that we would find behind the windshield of our favorite self-driving vehicle. Existing conventional camera systems have in common that they're relatively compartmentalized systems, with light coming from a scene being focused by a set of refractive lenses on a flat sensor surface, where that light gets digitized, and the digitized image that we read out from such a sensor is then processed by an image processing pipeline, the ISP, which can output, after a set of fairly involved image processing operations, an image that we can display and show to a user. That's not the only thing we can do with it. We can also analyze that image and use modern neural networks to, for example, classify the image content, find objects, or predict depth from that particular image. Modern neural networks have been super successful in analyzing images by the fact that these are differentiable algorithms. Learn the parameters of those algorithms by providing a training set of training images and output labels to learn the algorithm parameters. If you look at the other blocks of the camera pipeline, that's not the case. The ISP, the sensor, the lens, these are all blocks that are not differentiable. And that in a way limits us today to supervise all of the edge cases that we have to handle in a camera system, be that noise, be that low light scenarios, illusions, other imaging scenarios with our downstream neural network. Because that's the only block in the overall imaging chain that is actually differentiable, that we can utilize to handle these edge cases. So departing from that, I propose a set of approaches that allow us to make cameras differentiable and then try to aim towards learning the entire camera. So we'd replace the optics and the sensors, differentiable proxy functions that we can train together with a downstream neural network with first order stochastic gradient descent methods as if they were part of a giant neural network, and then optimize them also for a given downstream loss, be that an image output for display purposes or an IOU loss for an object detector. We can even do that for the illumination itself and make that part of our camera that we optimize over. And Sungwon later in the course will give you some examples of that powerful approach to design cameras in an end-to-end fashion. All right, this was pretty abstract, so let us have a look at a few examples of how we can make blocks of the camera system and then eventually the entire camera system differentiable. First block that I want to look at is the ISP. So as mentioned before, ISPs contain many processing blocks with a large set of discrete and continuous parameters that have been designed by imaging experts to process a raw image such that we get a nice, visually pleasing output image that is presented on a display. Now, these parameters and the algorithms itself, to a large extent, get tuned by algorithm experts according to the output of a set of metrics that you can measure from charts that you display to a camera and by the input of golden eye experts, which judge subjectively whether the resulting output images are good images, if they're visually and subjectively pleasing or not. This process of the iterative tuning can take, in fact, month and month for a given ISP. tedious process that involves visual inspection. One question that we wanted to investigate is whether we can come up with a differentiable approximation, so a differentiable proxy function that approximates the behavior of the ISP. So it takes as input a raw image and output image depending on a set of parameters. And if that proxy function is differentiable, then we can maybe use traditional first order stochastic gradient descent methods, similarly how we train modern neural networks, to optimize the parameters for a given loss function. We do this in two particular stages. So we first learn a differentiable proxy function, and then we optimize the parameters for a given proxy function. So let us have a look at that in more detail. I want to start with describing how we can learn a differentiable proxy. So to train any proxy function, the first thing that we need to do is to acquire training data. And this is done by taking a black box ISP, illustrated here with the black box, and giving it an input set of raw images and sampling over the parameters of the ISP. That provides us then a set of output images, illustrated here on the right side, that we can now use to train image-to-image network to produce from a set of the same raw images, the same output images that we previously sampled from the hardware ISP. So again, for a given input raw image I and given parameters, we learn a neural network to produce the corresponding ISP output that we got from hardware ISP. The particular neural network architecture that we use is a modification of the very popular UNet architecture, where we concatenated the parameter set with a bunch of tweaks to the individual down layer on the encoding stage of the neural network. This image-to-image network, once it's learned, can be fixed, and then we can optimize hyperparameters for a given task. All right, so how does that work? Let us have a look at the second stage. As mentioned, we fixed the hyperparameters of our network, which would be the model weights itself, and that does not include the input parameters of our ISP here. Those are in fact parameters that we can now optimize through stochastic gradient descent. We define a loss function on the output of the proxy that penalizes the distance, the output of the ISP to a specific target, let's say a simulated output target that we got a corresponding raw image from. Now, we can take our differentiable proxy module and, via first order stochastic gradient descent, optimize parameters that make the output as close as possible to the specific target that we want to optimize for. And we have broad flexibility on the target that we can choose. So we can look at different target applications. First application that I want to look at is optimizing an ISP for the output on a display. So produce natural images that are pleasant to a human viewer. The particular hardware ISP that we use is an ARM Mali C71 ISP, which is a state-of-the-art automotive ISP, which has over 30 continuous and discrete parameters. It's non-differentiable and very tricky to tune by human experts. And here's an example of the optimization procedure at work. Optimizing towards the target, a simulated target in real time, as we optimize, as we regress over the parameters to adequately fit the proxy output to the target. If we define a perceptual loss function on the output, we can now train parameters that produce visually pleasing outputs to a human viewer. And this allowed us, in fact, outperform manual expert tuning. So we show a side-by-side comparison where the manual tuned result shown on the left side and the automatically tuned proxy result on the right side. And in fact, 3 months of expert tuning were not enough to outperform our proxy tuning results, which in automated fashion, mind you, sampling tens of thousands of times, the particular learn proxy function, for even quantitative, traditional image quality metrics, measure detail accuracy, color accuracy, and more. So overall, this proxy optimization approach turned out to be a really effective strategy to tackle optimization of hardware ISPs. Now, let's have a look at a different downstream task, for example, object detection, remote use cases. Here you see an optimization time lapse where the optimizer is finding parameters that maximize mean average precision and mean average recall as plotted here on the right side. And you see here already in the images shown on the left side that the resulting ISP parameters strongly boost contrast around object discontinuities, which is something that intuitively we know for object detectors is beneficial. So overall here, intersection over union, measured after object detection of faster RCN and object detector, combined with our optimized ISP, produces the best results after optimizing with our proxy optimization approach. And here's an example where we do a side-by-side comparison with such an optimized ISP, object detector, with a state-of-the-art system, which is Tesla's Model S autopilot system, shown here on the left side, which in fact also uses radar for the perception system. And you see that in such low-light scenarios, especially at the peripheries, although we as researchers don't have access to very large data set and very large annotation crews such as our Tesla autopilot team, we are nevertheless able to get robust detections in a frame-by-frame approach without any tracking and additional post-processing on top here. So it hopefully illustrates how powerful it can be to optimize other blocks aside of the downstream neural network for a particular downstream task, such here as in this case object detection. So it motivated us to look at other blocks in the camera pipeline. And particularly, the next block that I want to look at is sensor control, which is sort of one step down from the ISP. How do we actually control exposure on the sensor, and how do we do that in a differentiable fashion? Exposure control can be pretty tricky, especially if you look at driving scenarios such as the one shown here, where we're driving through a tunnel and exiting a tunnel where we have a really high dynamic range that our sensor has to handle, and it's not able to capture that entire dynamic range from ultra low light scenarios inside the tunnel to bright sunlight outdoors. One cue that we can use as features is the histogram data. We can actually compute them at multiple resolutions over a grid. That provides us some distribution of the image intensity measured over different spatial regions of the sensor. We can assemble such multi-scale histograms and use them to predict exposures. If we combine a 1D CNN that is applied on these multi-scale histograms with fully connected layers, this provides actually an efficient model to predict exposure settings, which is in sharp contrast to traditional heuristic designs that use average-based auto-exposure changes. Now, we can go one step further and also add semantic features. So let's say we have a ResNet-based architecture for object detection that would produce bounding box. We can actually take features of that detector branch, combine them with the histogram branch, and use that entire model to predict, based both on semantic features as well as global intensity information, the exposure setting for the next frame. All right, so this seems like a first reasonable network architecture to predict exposures using semantic features and global intensity features. But how do we actually train this particular network? We can do a trick and use a second separate HDR camera that allows us to simulate exposures given the input HDR frame and artificially misadjust the exposure. And if you have such a frame, then we can use that wrong exposure to predict an exposure such that in the next frame our object detector is able to adequately detect a vehicle in the frame. So again, we use an IOU-based downstream loss to train our detector of interest. And this makes a pretty big difference in practice. So here we see driving out of a tunnel with our learned auto exposure on the left side and average space state-of-the-art auto exposure on the right side. You see that in such extreme illumination changes, learning the auto exposure in a differentiable fashion can be highly beneficial. As you see here on the left side, we're able to adjust very efficiently to such radical changes in intensity and detect, for example, the traffic light on the very left side here. Here's the same scene again, and you see how quickly auto exposure can adjust to these scenarios driven by downstream IOU losses. So now that we've looked at hardware ISPs and sensors rekindled as differentiable blocks, I want to get one step further and look at how we can make compound optics at the very beginning of our imaging system differentiable. Modern compound optics are designed in a box by imaging experts such as these fine gentlemen here, which use optical design software such as Code 5 to optimize the optics in isolation from the remaining imaging system. So here you see an optic being optimized for spot size alone. And these compound optics design systems have a huge benefit that there's a very large set of default designs online, and they're easy to use. They employ a lot of heuristic merit functions and black box optimizers. Nevertheless, as with the ISPs and the sensors from before, these systems are non-differentiable and we cannot pass gradients through an optical design. So we cannot easily optimize a particular design for a downstream task. So we can actually make also this step differentiable by modeling the spatially varying point spread function that is illustrated here in an efficient and differentiable manner. The shape of the PSF illustrated here depends on the lens profile, is defined by the lens radius, lens coefficients, the lens spacing between the individual lenses, and the particular material of the lenses. We can use modern ray tracing based design software that has these rich catalogs of optical systems to produce output PSFs. So for a given parameter setting and a particular field, a particular position on the sensor, we can produce a PSF and a vignette factor. Now, we can try to model that particular PSF with a differentiable proxy for our ray tracer, which takes as input, again, the parameters, the particular position on the sensor, and then predicts a PSF and that particular vignette factor. It can train this particular proxy function by penalizing the difference to a set of ground truth simulated PSFs and vignette factor from the optical design system. The particular network architecture that we use is an MLP that creates low-dimensional features and a convolutional decoder. This approach of modeling the aberrations rather than an image-to-image approach turns out to be much more accurate and providing us good gradient signals for optimizing compound optical systems. All right, so we vary the parameters of the optical system to generate PSF data that we then use to train our proxy function. After the design, we fixed it finally. So here's an example of the optimization process at work. The task loss that we use here minimizes the spot size. We can see that it can actually outperform Cmax at its own task, which is minimizing the spot size. And all of this is done on a proxy function using first order stochastic gradient descent. Now we can not only minimize spot size, but we can also implement domain-specific optics for different tasks. And here I want to look at 3 different tasks. The first one would be natural image capture. So here we define a task function that places a perceptual loss on the output of the raw image that is captured by a simulated optical system plus sensor, and then piped through an ISP. And what you see here, particularly look at field around 8 degrees, is that instead of a longer tail for a nominal design that comes straight from Zemax, we get a much more peaky design at the cost of a tiny valued floor. And this actually results in fewer aberrations in the periphery. So you can see visually that the resulting images, when displayed, are more pleasing to a human viewer. Now, for an entirely different task, which would be object detection, we can see that we get an entirely different behavior if we minimize intersection over union as an output of an object detector. This leads to a very uniform PSF, which is beneficial for the detector, which does not have to tailor its output to the spatial position of the sensor for given proposals. This results in better performance in the wild, where we reduce false negative and false positives as compared to the normal optic on the left side. Finally, an entirely different task is traffic light detection, where you see a behavior which is sharper to the center of the visual field because a lot of overhanging traffic lights are visible from far away at a long distance. So here the optic is optimizing towards these traffic lights at very long distances, because at closer distances they're easier to detect, even with the larger blurs. And this also results in better performance for traffic lights. Here you see that, for example, the red traffic light is properly detected, and the traffic light straight is also adequately detected when looking at the end-to-end optimized design. So hopefully with all of that, I've convinced you that it is worthwhile to rethink the design process of camera systems in an end-to-end fashion, where we make individual blocks of our camera system, be that the optics, the sensor, the ISP, and the downstream neural network differentiable, and train them in an end-to-end fashion jointly together, which can provide us with better performance for existing tasks, but can really also tailor towards task-specific cameras that allow us to bring superhuman vision capabilities to camera systems of tomorrow.
Hello everybody, my name is Ethan Zhang, and in this portion of the course, I will be talking about Nano-Optics for high-quality, thin lens imaging. This course covers our recent work on using metasurfaces to design tiny lenses, which could pave the way for smaller and lighter cameras. All of the information in this talk can also be found on our project website. Alright, so let's begin with some context. Smartphone cameras are becoming more sophisticated and complex with each passing year, resulting in bulky camera bumps on consumer devices. This is an excerpt from the Apple September event in 2018. And here you can see that even the latest smartphone at that time had quite complex optics inside of its camera. The optics consists of this series of glass lenses, each of which is combined together provides enough optical bending power in order to produce crisp images. But this optical stack here ends up producing the nasty camera bump that makes smartphones become increasingly bulky. And it's not just Apple that has the camera bump. Today, most commodity smartphones exhibit a camera bump that houses the compound optics that are necessary for taking high-quality pictures. Doesn't matter if you're using an Apple iPhone or a Google Pixel, we're starting to see this camera bump appear across pretty much all commodity smartphones today. Going beyond smartphones, almost all applications that rely on cameras will also face the same problem. Bulky, compound optics are used to capture and focus light in order to take pictures of the real world. And navigating the trade-off between image quality and physical form factor is a perpetual engineering challenge. In this work, we present metasurface optics as a replacement for bulky compound lenses. Metasurfaces are a material that can provide the same optical power as a compound optic, but with a much smaller form factor. Here, on the left, we show a real fabricated metasurface on a human finger, just to provide a scale of the sizes of these metasurfaces. And on the right, I show a diagram of the metasurface. Here, in the diagram, you can see that the metasurface consists of tiny nano-antennae, or nanopillars, and these nanopillars are what modulates the incoming light. Okay, so more on how this works. While a conventional optic relies on a series of glass lenses to bend and steer light, as shown on the left, a metasurface uses sub-wavelength nano-antenna to direct light with much finer control. A single metasurface provides much more possibilities for shaping light waves than curved glass. The modulated wavefront can then be interpreted and processed by software to produce high-quality imaging results. In our work, we jointly design metasurface optics and software processing using AI techniques, allowing us to produce Nano-Optics. Although metasurfaces have been seen as a promising alternative to glass optics, perhaps for at least a decade, prior methods have not been able to demonstrate sufficient imaging performance. One technique, called dispersion engineering, which we show on the left, is able to create images with high quality, but only with a small field of view and a small aperture size. Other methods, such as those employing heuristic designs, have been able to achieve larger field of views and larger aperture sizes, but they fail to achieve good image quality. So in the past, works that have been done in the metasurface literature are able to get some, but not all of the qualities needed for a good imaging device. You can get high image quality with dispersion engineering, but you don't want to sacrifice aperture size and limit your field of view if you really want to make a practical imaging system. In this work, we present Nano-Optics, which significantly outperforms the previous state-of-the-art, as shown in this side-by-side comparison of imaging performance. Our method is the first meta-optics imaging approach that achieves high-quality, wide field of view color imaging with a large aperture size. And I'd like to emphasize that this video you see here is completely experimental capture. Basically what I mean is that we captured an image with our fabricated metasurfaces, and then we post-processed the result in software. This is not a simulation. Okay, so now I'll go more into the design framework of Nano-Optics. Nano-Optics consists of two primary components: the metasurface optic and the software correction, which we refer to here as deconvolution. Here, our metasurface simulator is parameterized by the metasurface parameters P sub meta, and the aberration correction is parameterized by the deconvolution parameters P sub deconv. We will explain both parts of this pipeline, starting with the metasurface simulation. Our metasurface simulator operates by generating spatially varying point spread functions, or PSF for short, and these PSFs encode the aberrations produced by the meta-optic. And just to provide some more information, the point spread function is essentially the response of the optical system when you shine a flat light wave onto the metasurface. And these PSFs are used as a sort of measure to show what kind of aberrations that you would expect in the metasurface or optical design. Simulating the PSFs in order to quantify the metasurface performance is typically a time-consuming process. However, in this work, we propose a proxy simulator that speeds up this simulation process. Our proxy simulator works in a series of steps. First, we define a polynomial basis function that describes the phase response for a single wavelength, for example, the green wavelength. We then determine the corresponding nanopost structure of the meta-optic that will impart that specific phase response for that wavelength. And this mapping is performed by using a proxy function, which we call phase to structure. More on that later. Now, given this nanostructure, we can then infer the phase response at the other wavelengths using rigorous coupled wave analysis. And this allows us to define a multi-wavelength phase function, which we call structure to phase. Again, more on that later. Which we then diffract to determine the electric field. From the electric field, we can then determine the spatial PSFs. Each step of this simulation pipeline is fully differentiable, allowing for gradient flow back to the optimization parameters. Here, gradient flow is shown by the blue arrows. And in order to design this system in an end-to-end manner, it is essential that the gradients are able to flow all the way back to the design parameters from the spatially varying PSFs. This entire chain here is 3,000 times faster than traditional full wave simulation. And this allows us to run our design process much faster than previous methods. Okay, so now I will go more in depth onto the individual components of the simulation. First, the phase to structure mapping determines the thickness of the nano antenna on the metasurface, which we refer to as the duty cycle. This equation that you see here relates the duty cycle, dr, to the phase of the metasurface at the nominal wavelength, which we call phi r. Specifically, given the phase phi at the nominal wavelength, this equation will determine the duty cycle of the metasurface that will impart that phase response for that wavelength. This function needs to be injective, so we set the design wavelength to be at the blue wavelength in order to avoid injectivity issues caused by phase wrapping. The coefficients b sub I are set specifically for this nominal wavelength. And this equation is implemented by the following example code, which can be found on our project website. Next, I will explain the mapping from duty cycle, or structure, back into phase. Now that we have a metasurface structure from the previous equation, we want to know what the phase response is at arbitrary wavelengths within the visible spectrum. The true phase response as a function of duty cycle is determined through rigorous coupled wave analysis, or RCWA. This equation here approximates that true response, and the coefficients c are set to maximize the accuracy of that fit. Again, this equation is implemented by some example code, which we show here, and all of this code can be found on our project website. Okay, that covers the Meta-Optics simulator, which is fast and differentiable. And with our Meta-Optics simulator in hand, we are able to simulate what the sensor ought to measure in an efficient and differentiable manner. And what I mean to say is that if we were to have a certain metasurface design, then our differentiable proxy simulator could tell us what we expect our camera sensor to see if we were to fabricate that metasurface. Now, we will describe the second component of our nano camera design, the deconvolution algorithm. As you can see here, even if we have a good metasurface design, the measurement on the sensor might still be aberrated or blurred out, and we need a deconvolution algorithm in order to correct for any residual mistakes. Okay, there's a wide variety of deconvolution methods out there. Classical deconvolution methods, such as Wiener deconvolution, and optimization-based methods, such as ADMM, perform Fourier space inverse filtering by using the PSF. Employing knowledge of the imaging system through the PSF makes these methods highly generalizable. However, they can often accentuate sensor noise as shown here. Furthermore, these algorithms have limited design freedom because they don't employ very many free parameters. In contrast, recent works in deep learning have shown that neural networks can also perform deconvolution, and that their rich design space can enable learning of a wide variety of features that facilitate reconstruction. However, their performance on unseen examples is oftentimes inconsistent, and these methods cannot handle very large aberrations. In order to remedy this, we combine these two domains. We propose a feature-based deconvolution method that employs a traditional inverse filter together with neural networks for feature extraction and refinement. This combination allows us to learn effective features that facilitate the inverse filter's deconvolution while still utilizing the knowledge of the PSF to promote generalizability. And here is some example code from our deconvolution algorithm. We apply a few convolution layers in order to extract features, which are then fed into the inverse filter, which in this case is a Wiener filter here. Again, the full code can be found on our website. Finally, putting everything together, we get our end-to-end imaging pipeline. During the design stage, we employ stochastic gradient descent optimization in order to design the parameters. After optimization, these parameters are then fixed, and we use the parameters p sub meta to fabricate the meta optic. And then we use the parameters p sub deconv when we operate our imager. Here we show an optimization time-lapse. As our optimization progresses, the meta-optic imager converges upon a setting that minimizes image error across the field of view. Because of our efficient end-to-end image simulator, this entire training process can be completed within a single day. Here I show an example of the fabricated metasurface on the left compared to a grain of rice. This is just to show you, again, the scale of the size of the metasurface. On the right is a picture of the experimental setup that we use to demonstrate the imaging performance of the metasurface. Our experimental setup consists of a conventional CMOS sensor, a metasurface mount for holding the metasurface, a relay system used to magnify the image captured by the metasurface so that it can be seen by the CMOS sensor, and an OLED display for displaying images. Here's a schematic of the same setup. The relay system here is used to magnify the image before it arrives to the CMOS sensor. The raw measurements captured from the camera are then fed into our computational reconstruction algorithm. This diagram can be found as part of the supplementary information in the paper. And here's a schematic of the PSF measurement setup. Because of manufacturing imperfections, the PSF of the fabricated metasurface deviates slightly from the PSF that we expect from our simulations. To compensate for this error, we acquired a real PSF of the fabricated metasurface, and then we use that PSF to fine-tune our deconvolution network. The PSF acquisition setup is very similar to our imaging setup. The metasurface and relay system are kept exactly the same. We only replace the OLED screen with a collimated LED and pinhole. With the LED and pinhole, we can construct a laser point source for each wavelength, allowing us to measure the PSF for each wavelength. This diagram can also be found in the supplementary information of the paper. Our optimized meta-optic design meets several design criteria that were not met by previous methods. Recall the dispersion engineering methods from before. Those methods were not able to achieve large apertures. However, our aperture in this work is the largest demonstrated so far for meta-optics for imaging at 500 microns, which allows for increased light collection. We also achieve a large field of view at 40 degrees, and our optic also exhibits a low f number, which means that the optic can be placed extremely close to the camera sensor, and this is important if we want to build a small camera. Furthermore, we are able to capture images within the visible spectrum. No previous metasurface has demonstrated imaging with this combination of aperture, field of view, f number, and fractional bandwidth, referring to the visible spectrum. And this is because previously achieving any one of these metrics came at the cost of some other metric. For example, one could achieve a low f number by sacrificing the aperture size. To formally quantify our design specs, we propose a new metric called the diffractive lens achromatic capacity, or DLAC for short. This metric is a product of Fresnel number and fractional bandwidth, and can only be maximized by satisfying all of the design specs. Because of the trade-offs made by previous methods, almost none of them meet our design capacity. The only previous work that comes close to our design specs is the work of Shane Colburn from 2018. We will next show full color imaging captures that compare between the ones captured by Shane from 2018 and the ones from our Nano camera. Okay, so here's a side-by-side comparison between the two methods. Our Nano camera on the right clearly demonstrates significant improvement in resolution, color accuracy, and reduced aberrations compared to the work of Colburn from 2018. Here's another result, a still image, showing again the achieved improvements of resolution and color accuracy. And here is yet again another still result. We also perform a spatial resolution test using a Siemens star chart. Our Nano-Optic imager achieves accurate performance across all color channels, as you can see on the right, whereas the previous method exhibits severe aberrations. Okay, so now that we have shown that Nano-Optics can outperform the previous meta-optic imager works, how does it compare against a conventional imaging system using refractive lenses? So now we will show that Nano-Optics can achieve a very similar quality as a conventional camera despite being over 500,000 times smaller in size. So here are some side-by-side comparisons of full color captures by both the conventional camera and the Nano camera. And we can see that although the Nano camera is not perfect, there's still some room for improvement, we see that is quite close to the performance of the conventional camera, which uses highly corrected compound lenses. And here's another video result, which shows that we can achieve high quality color results comparable to the conventional camera on diverse scenes. Here's a still image result comparing the compound optic and the Neuro-Nano optic. Again, we see that although the Neuro-Nano optic is not perfect, it is able to achieve a lot of similar resolution and color accuracy as the compound optic on the left. And again, here's another still result showing similar performance. We again performed a resolution test by using the Siemens star. And as you can see, we achieve a similar resolution quality across all wavelengths as the conventional camera, despite the Nano optic being orders of magnitude smaller in size. And here I'm showing some more comparisons against alternative metasurface designs. Starting from the left, the hyperboloid design is designed specifically for a single wavelength, in this case the green wavelength at 511 nanometers. Although the performance is good for that wavelength, the imaging quality at other wavelengths is very poor. And applying a simple Wiener filter doesn't improve the performance much, as can be seen in the next column over. The middle column shows the work of Coherent from 2018 again, which also uses Wiener filtering. And as we showed before, the work from the imaging quality from that work also still exhibits a lot of aberrations. The next two columns show what I've shown already, the Nano-Optics imaging result at the different wavelengths, followed by the ground truth imaging result using the conventional compound optics lens. Overall, Nano-Optics is able to achieve the best performance to date for metasurface imagers. Okay, so that mostly concludes the imaging performance that I wanted to talk about for Nano-Optics. And in this slide, I just wanted to talk about the fabrication of these metasurfaces and how we can go about making a lot of these metasurface imagers at scale. So in this work, we fabricated the metasurface through electron beam lithography, which is good for this work here, but is somewhat of a slow process. In order to scale production to a commercial scale, we can leverage IC manufacturing techniques such as deep ultraviolet and immersion lithography. Going forwards, we believe that metasurface imagers could become commercially viable through these manufacturing processes. That concludes my segment of this course. To summarize, we presented Nano-Optics, a nanoscale camera that we built by co-designing a single meta-optic and software correction, and we achieved full color imaging with quality comparable to commercial cameras. We hope that this work can inspire more research and development into metasurfaces for imaging and beyond. For more information, including example code, please visit our website.
Okay, I'm Seung-hwan, and today I'm gonna be talking about differentiable illumination and temporal sensing. Okay, let's get started. Before diving into the details, let me first introduce myself. As I just mentioned, I'm Seung-hwan. I just joined as an assistant professor at Posttech, and I'm studying how to capture, model, analyze, and exploit light waves for graphics vision imaging and display. So my specific research interests or research areas include differentiable camera, time-of-flight imaging, reflectance imaging, hyperspectral imaging, polarimetric imaging, panoptic imaging, holographic display, neural visual representation. Okay, and today, specifically for this session, I'm gonna be mostly talking about this differentiable illumination and temporal sensing, which includes both differentiable camera design and also time-of-flight imaging. And then let me give you the high-level overview about what is differentiable illumination and temporal sensing is. So here in our modern imaging systems, we not only have a camera but also illumination modules, right? And then here in this example of mobile phone, we have a flash that we're gonna emit the light to a scene. And then the light, we're gonna travel the scene and finally reflect it towards this camera. Then the light will gonna be gathered by our lenses and then focused down to a sensor. Then the sensor records the instant light energy and generate a form of image, such as this nice chameleon image. Then we have amazing post-processing algorithm these days for instance, in a form of a neural network that estimates the many properties of a scene or even understand and infer some of the information hidden in this scene. Then, for instance, in this example, our neural network estimates the class of the image, and here our neural network predicts that here we have a chameleon in this image. Then, in order to make our neural networks to do this task, we train this neural network using a loss function based on the output of the neural network, which supervises or trains this neural network via backpropagation. And then in this regime of differentiable camera and display, what we want to do here is we want to optimize our imaging system that includes this illumination module and also jointly optimize our neural network for post-processing algorithms, right? And here, this will gonna innovate the existing illumination designs of our cameras, and even the optimizes our entire the hardware and software imaging systems from the illumination to the scene and back to the sensor, and how to process that to acquire hidden information of the scene. This is the essence of differentiable illumination. I'm going to provide two specific examples of this differentiable illumination research. And the first one is about differentiable time of flight. And this is a joint work with Ilya, me, and Chang, Wolfgang, and Felix. This work was published at CBPR 2021, and the original paper's title is Mask TOF, Learning Micro-Lens Masks for Flying Pixel Remover in Time-of-Flight Imaging. So let's first begin with a general introduction on the time-of-flight imaging. In our natural systems, even in one of the man-made systems like submarine, we can see exciting ways of estimating the distance or depth from a scene to our imaging sensor, right? We can do that by emitting some of the sound from an imaging system or from a system to a scene, and then measure how long does it take from the sound reflected back to the imaging system, right? By measuring this time of flight, we can understand or we can measure the distance between the imaging system and then the obstacle. So if we move our focus to the time of flight imaging cameras, what we do here is emit actually light to a scene instead of sound, and measure how long does this light take from its emittance and then traveling to the scene and then back to the camera. The basic theory is same. This time of flight information relates this distance between the camera and then the scene with the speed of light. Okay, so time of flight is equal to the 2 times of the distance between them divided by speed of light in this medium. There are many applications of time of flight imaging systems, and we can briefly categorize these time of flight cameras into 2 different ones. First one is the direct time of flight camera, and second one is the indirect time of flight camera. Okay, and direct time of flight camera offers the many interesting advantages, and because of that, we now have direct time of flight cameras in the mobile phones and autonomous vehicles, and even airborne devices that measures our terrain's geometric structure. Also, indirect time of flight cameras has its own advantages over direct ones as well, and often we use indirect time of flight cameras for the gaming applications or any human computer interactions or augmented and virtual in reality systems. And we often call indirect time-of-flight cameras as correlation imagers. And in this work, we're gonna look into the details of correlation time-of-flight imaging or indirect time-of-flight imaging. Here, the operation of a time-of-flight camera or indirect time-of-flight camera begins in the optical domain. Here, we illuminate a scene with continuously modulated light or illumination. What that means is that we modulate our illumination emitted to a scene has time-varying intensities in a sinusoidal manner. Okay, and the illumination hits some target scene. And if we zoom this a little bit, then you can see that our intensity of illumination is sinusoidally modulated, and then the light will gonna be reflected from the target to a sensor. And here, due to the travel distance from the camera to the target, we're going to have some phase shift between the two signals, right? And this phase shift encodes the actual distance from the time-of-flight camera to the target. And if we can estimate this phase shift, then we can estimate the distance or depth. Then once we capture this the reflected light using our time-of-flight sensor, then in the existing indirect time-of-flight camera sensors, we have a special sensor design which we often call as photonic mixer device, or in short called as PMD. And this PMD sensor, what it does is it first converts the instant photon energy into electron energy in the analog domain. And then this is the captured time-varying sinusoidal signal reflected from a scene, right? And we all know that now this captured signal has a phase shift with respect to a reference sinusoidal pattern, right? And then if we calculate the correlation between these two sinusoidal patterns with a phase shift, then what we can obtain is some constant value that corresponds to the specific phase shift, okay? And from the phase shift, we can estimate the depth. So here, the goal is we want to obtain this correlation value correctly. Then seems like we are all good and we can estimate the accurate depth information using this indirect time-of-flight imaging. But here still we have many existing limitations in this indirect time-of-flight imaging, and one of them is called as flying pixel. So let me first describe what the flying pixel is. Here we have a time-of-flight camera, indirect time-of-flight camera specifically. And in here, as I discussed, we have an illumination light source, and typically we use LED. And then we have a lens that we're going to collect the light reflected from a scene. And then, as in any lens system, we have an aperture that we're going to control how much light we're going to collect. And then we have a sensor here, right? That which consists of many pixels and, more importantly, micro lens array right in front of the sensor. Let's say that we have a foreground object and then background object in a scene, right? And then let's see what is going to happen for this indirect time-of-flight imaging when we estimate the correct depth. The LED will gonna flood our sinusoidally modulated illumination into a scene. Then our real-world scenes, which are foreground objects and background objects here, we're gonna reflect this illumination back to the camera, right? Then the reflected light will gonna be collected by our lenses, and then some of the light will gonna be blocked by our aperture, and then finally focused down to a sensor. So these blue lights all come from this our background objects, whereas this red light all come from this foreground object, right? And here, interestingly, at this particular pixel that we described, it collects the light both from the foreground signal and then the background signal, because we are capturing this this edge between the foreground and then background, right? And once we have this mixed light reaching to a single pixel, then we're going to have a problem, which we call as flying pixel. Let's understand it in more details. If we zoom in the sensor region, we have this red light coming from the foreground and then the blue light coming from the background. And they're going to be collected by our micro lenses, and then the one specific pixel, we're going to record just the energy of these instant photons regardless of its origins, whether it is coming from the foreground or background. We're going to just collect it and just record its intensity value. Then here, if we utilize this captured intensity to calculate the depth information using correlation computation, we're going to have some flying pixel problem. What is flying pixel here? So let's say that this is the x-axis, here is the measured depth, and then y-axis is the probability of estimating whether this is the correct depth or not. And then let's say that we want to, our target depth that we want to measure is the background one, here corresponding to the blue object. And that depth or distance from the camera is located further than the red one. However, since we have measured the intensity value as a mixed value between this foreground and then the background, then the estimated scene depth would locate at the in between this foreground and background, meaning that the pixel will gonna be appear as if it is floating in between this surface, meaning that, in other words, it is flying pixel. So it is a little bit straightforward to solve this problem, right? And which we can do by actually reducing this aperture size. Let's say if only this center light can pass through this lens system, then we're not gonna have any flying pixel problem because there is no light coming from the foreground reaching to this specific pixel. So in this case, we're gonna have this correct depth estimation at the true depth. But here, problem arises because of this reduced light energy entering only the center part of the lens. Because we have less and less light energy reaching down to this single pixel, we're going to have more noisy estimate, right? So because this pixel value becomes noisy with the less amount of light, then we are likely to measure the depth at the different location or different position than this true depth, right? It's more in a mathematical term, its standard deviation becomes, it's this spreadness of this measuring the depth probability becomes wider, right? So it's gonna be uncertain measurement, deviating from our true depth. Okay. And now we propose a technique to solve this problem, which we call as mask TOF, which, true to its name, augments this camera pipeline using a specifically designed the micro lens mask. So specifically here, this is the micro lens mask pixel, right? that exist between the sensor CMOS pixel and then the micro lens. All right, then let's see what's going to happen. If we have instant light to a micro lens, then the light will gonna be the occluded based on this micro lens mask pixel pattern, and then our CMOS sensor pixel will gonna collect only the light energy that passes through this mask. Okay, and this mask selectively blocks this instant light energy, and that allows us to effectively give each pixel its own custom aperture. Here, we can augment our camera to have spatially varying susceptibility to noise and flying pixels, right? And this leverage the denoising and deflying pixel local spatial neighborhoods. So what that means is, here, given this information of this micro lens mask, if the micro lens mask has a like this middle size shape, then it's gonna be it's gonna be just in between in between these trays of the noisy and then flying pixels. As we just saw, if the size of the aperture is quite large, then which corresponds to this case shown in here, if it is the case, then it is likely that we're going to have more flying pixels but less noise, right? However, if the size of the aperture is small, that looks like this, then they're going to give, for example, like this, then they're going to give the really noisy or uncertain depth estimate. However, it'll be free from our these flying pixels, right? Then implementing this in the micro lens level, we're gonna give us this diverse sampling of this with the different trade-off between the noisiness and then flying pixel problems, right? So here important is that if we have a global aperture that controls the size of the aperture, then we're not going to be able to obtain this diverse sampling. So what that means is, on this left side, this is the sampling result by this our global aperture. If you open your aperture to a large extent, then all of your pixels will going to suffer from the flying pixels, right? However, there'll be all the great samples in terms of the noisiness or certaintiness. Here, if you use just this global sampling using your aperture, using your global aperture, then there is no spatial information that you can make use of to resolve these flying pixels, right? However, if you use our specific strategy of this micro lens masking, and if we use this different per pixel aperture implementation, then we can make use of this diverse spatial information in the pixels with varying the trade-off between the noisiness and then the flying pixels to decode the problem of denoising and deflying. Okay, and zooming back out, now we passed this mask array and masked correlation images into a convolutional neural network, which refines our estimated depths to outputs a decoded depth estimation results. And here, note that what we want to do in a differentiable camera and display manner is that we want to find out the best design of our micro lens array, okay, in addition to the our refinement neural network. So here we calculate the error with respect to the ground truth depth. We can propagate this loss function through the neural network and then the mask pattern. Here, then, therefore, we can jointly optimize or learn this refinement network and the micro lens mask. In this way, starting at an initial mask iterate, we can simultaneously learn them, right? We optimize this micro lens mask, and also we optimize this refinement network. Okay, here, to fully validate mask TOF, we built an imaging prototype of this system, given the impracticality of accessing the sensor surface. Okay, we move the mask onto a virtual plane with a customly designed optical relay system, right? And we lithographically manufacture this mask pattern and mount them on a 3D translation stage for focusing. Okay, so here note that all of this why we did this is because of the difficulty of taking this sensor micro lens apart by ourselves. But for the actual time of flight camera manufacturer, for them it would be easy to place this our learned mask pattern right in front of their sensors, right? Here, just a proof of concept in research academic lab. We just optically relay this sensor plane to a virtual one. Then we placed a lithographically fabricated our learned micro lens mask on a free space, right? So here, this is the results from our method, and we captured a scene of this pumpkin. And if you just use the conventional time of flight camera that uses a wide aperture, they're gonna give you the high accuracy surface, the 3D depth information for the center parts of the object. But for the edge information, then you're gonna see lots of flying pixels around the edges, right? Because of the large aperture. However, in our case, shown on the right, this is our estimated results from the real prototype, showing that we were able to reduce this flying pixels quite significantly by utilizing both these learned masks and then our refinement network. And in total, we are able to reduce around 30% of the flying pixels. Okay, that was the first part of our talk. Okay, let me begin our second part of this session, which is differentiable active stereo. And this is a joint work with Felix. And the work was presented at CVPR 2021. Title is Polka Lines, Learning Structured Illumination and Reconstruction for Active Stereo. To explain our work, let's first begin with the definition of phase of light. Phase is the offset of a light wave with respect to a certain base. Okay, and phase is invisible to human eyes, as we can only sense the intensity of light by integrating the different lights with different phases. So, however, actually phase is everywhere and can be utilized for specific purposes. So here, let's say that we have an instant light wave onto this glass. Then light wave slows down inside of the glass because of the refractive index difference between the glass and then air. Then this induces phase delay to the excitant light after passing through this glass, denoted here as red arrow. And this phase shift can be described mathematically as an equation shown in here. The phase delay phi is equal to the wave number k multiplied by this refractive index difference eta and the height of this glass h. And now, if we have another glass with different thickness, then phase delay becomes different because of this equation here height is different, right? Then this results in phase shift between these two light waves. So diffractive optical element, called DOE, consists of micron-scale million number of glass slabs with different thicknesses. So this allows us to spatially modulate the phase distribution of instant light waves. So one of the applications of this DOE is depth imaging. So here, depth imaging, we want to use it for the various applications, including the AR, VR, robotics, and this autonomous vehicle to understand the 3D structure of our neighboring scenes. So active stereo system is a cornerstone depth imaging modality for its low cost and robust depth estimation performance. So active stereo systems consist of stereo cameras looking at a scene, and it also has a structured illumination module consisting of a laser illumination and a DOE. And this DOE is designed to produce a specific illumination image to a scene. Then this illumination pattern is engraved to a scene as a light source. Then this illumination pattern are captured also by our stereo cameras. The captured images from stereo cameras now contain both scene texture and illumination patterns on top of the scene, right? Then we estimate the depth information by matching correspondence between these two images. Since we have additional illuminations projected onto a scene, we can make use of them in addition to the scene texture to build this correspondence mapping, which is converted into a depth information for each pixel. So this reconstruction algorithm therefore make use of both scene texture and illumination pattern. Here, as shown on the top right, our depth information G can be obtained with the known focal length of the lens, stereo camera's lens, and then baseline B, which is the distance between the two stereo cameras, and the disparity D, which is the displacement of pixel location between the left camera and then the right camera. Then let's look at the conventional design pipeline of active stereo depth imaging systems, which has a pipeline design framework. So first, what people have been doing so far is we hand engineer or set the heuristic measure of the illumination pattern for their optimal performance measure. And for example, to optimize their randomness of the pattern while maintaining their the fabrication the easiness. And once they obtain this illumination pattern, then they develop the reconstruction algorithms to obtain the best depth accuracy as much as possible from the fixed hardware system. Here, fixed hardware system means that the illumination pattern itself is fixed. So on the right-hand side, we show a 2D graph about the expected depth error. And the x-axis here, the horizontal axis, is the reconstruction algorithm, the space of the possible reconstruction algorithms. The y-axis here describes the space of the illumination images possible, right? And then as you saw, in the conventional pipeline design, we first only the scan through this illumination image space and find the best one. And then once that is fixed, we search for the potential reconstruction method using the neural networks or any other methods. So here, to overcome this, the sequential the limitations of the sequencer design, which is that we may not find the best optimal solution, best optimal combination of illumination, image, and reconstruction algorithm for giving this best depth accuracy. What we here propose is to jointly optimize our illumination, image, and reconstruction algorithm to find the better the depth the expected better depth accuracy by jointly estimating the illumination, image, and reconstruction. Okay. Here, in order to do this, our key idea is to have this differentiable flow from the DOE to the reconstruction results and optimize both illumination and reconstruction. Let's say that we simulate the illumination pattern and stereo images for a given DOE phase map, like this. Then we estimate depth information using a reconstruction method in a form of a neural network. Then loss is computed compared to the ground truth, and the loss is backpropagated all the way up to the DOE. Then this backpropagation based optimization, note that here the backpropagation based optimization requires the differentiability of the image formation model here and our the differentiability of this our reconstruction algorithm. Okay, then let me now introduce how we could make these two differentiable so that we can optimize both DOE profile, which is a DOE phase map, and then reconstruction algorithm jointly. So we introduced a differentiable simulation for active stereo image formation model. So we emit the light from a laser passing through DOE, right? Here everything is in simulation. Okay, and we emit the light passing through the DOE to a scene. And this DOE, as I described, is parameterized as a phase map, which corresponds to a specific height map of the DOE. Then, if we have this DOE phase map in our hands, then we can calculate what kinds of illumination image would be projected to a scene based on Fourier optics. So here, as taught in our course, we use the far field propagation, specifically Fraunhofer propagation, in order to obtain this illumination image. For example, here, for the explanation purposes, this illumination image I, let's say that this one corresponds to this DOE phase map, calculated based on the equation that I just showed before. Now, as we have this illumination image and then the virtual scene asset, including the depth information, normal information, and its the albedo, then we can simulate the captured images from the stereo cameras, given this scene illumination image. Okay. Then we can calculate these stereo images where the scene this DOE illumination is projected on top of the scene using geometric optics, specifically epipolar geometry. Now that we have simulated the sensor inputs, we reconstruct depths by estimating correspondence between the images. So here we develop a neural network method that exploits the known illumination being optimized different from the conventional stereo matching networks. Here, in more details, from these two stereo images, we extract their spatial features using a feature extractor, and also we extract feature from the illumination image. Then, given these features of these three images, we construct two cost volumes for the wide baseline image between the stereo images, and also we construct another narrow baseline cost volume with a stereo image and an illumination image. Then, using these informations, both we estimate the depth at a low resolution, which is upsampled to a higher resolution using a convolutional upsampler. So, as both image simulation in the form of differentiable image formation and our reconstruction, which is a neural network, are differentiable now, we can backpropagate the loss to the neural network and then to the DOE phase map, right? So now we can estimate the best optimization parameters for the DOE phase map and reconstruction to make our estimated depths as close as possible to the ground truth depth information. So this is the result. So as a result of our computational end-to-end optimization of illumination and reconstruction, so we obtain this interesting illumination pattern, which we call as polka lines, right? And as the name suggests, this polka line illumination pattern consists of small-sized dots slanted along a certain direction, and it has varying intensities for inside of this each slanted dots, right? And at the center, we have some dots has high intensity, and some other dots have the low intensities, and it has very high density for sure. So for comparison, this is the conventional hand-designed illumination pattern from Intel RealSense D415 sensor. And it has a regular structure with constant the intensities with large size dots, right? And as this is not directly optimized for improving depth accuracy, it often fails for challenging scenes as shown on the right. This is the estimated depth in simulation. So in contrast, our learned illumination pattern enables accurate depth estimation shown on the right. So we fabricated the learned DOEs using a photolithography technique and built a prototype system that experimentally produces the polka lines illumination patterns shown on the left. So here we used two NIR stereo cameras and built our illumination module with an NIR laser, collimated light, and also there is the mounting device that holds our fabricated DOEs. So our prototype system can acquire accurate depth information for challenging scenes, including the textureless surfaces under diverse environments, from indoor illumination to outdoor sunlight. For example, on the most left side, we put multiple objects on an optical table in an indoor lighting illumination condition with our fluorescent light. Also, that is the second one is me wearing a t-shirt and with my fingers free, and that is also captured under the indoor lighting. In the next example, in the third column, we captured a textureless box without any ambient illumination in an indoor condition. In the fourth column, we captured a notebook under the sunlight, but still in the indoor condition. On the most right-hand side, we bring our imaging system to the outdoor condition and captured myself, my body, under the sunlight. Okay, our system also runs in real time. We capture challenging objects such as low reflectance diffuse bag and a specular stop sign, a color checker, and a transparent bubble wrap. And as you can see here. So we also tested our what kinds of patterns that we could optimize for the different environments. So what we call this application is we call it as environment adaptive illumination design, which means it is very easy to obtain the optimal illumination patterns for the different simulation environments, such as the different laser power, different ambient light illumination, different noise statistics, and so on and so on. If we feed these different simulation environments into our end-to-end training pipeline, then we can obtain the corresponding illumination pattern. So this is the result in simulation. So if we in the first experiment, we tested the impact of ambient light. So if the ambient light is low, if the ambient power is low, then as you can see on the most left-hand side, the optimized illumination pattern becomes more dense with low intensity. However, as we increase the ambient illumination power on the most right-hand side, then you can see that this intensity of each dots becomes higher, and the dots are getting the sparser. So this is because in the high ambient light situation, the illumination pattern should stand out of the ambient light, so it becomes higher in terms of intensity. And in order to do that, we need to sacrifice the density of the projected dots a little bit because our power budget is limited. So the entire the dots are getting a little bit sparser. Also, we tested the impact of our noise. For instance, like if we have the large aperture size of the camera, that is going to allow us to have the less noise. However, if we have the really small aperture of the lens system, then we're going to likely to have the high noise. Or you can think about this the other configurations where the noise varies, such as if you bring your system into the low light condition or in a different configurations. Then in that case, if you have the moderate degree of noise shown on the left, then we're going to have really dense the illumination patterns. And on the right, if we have the high level of noise, then in order to stand out of this noise level, our illumination pattern also becomes sparser and with the higher intensity. Okay, and these illumination patterns optimized for the specific environments could provide robustness of depth imaging in the extreme scenarios. And depending on the user's the preferences for the environment, we believe that this environment adaptive illumination design could be very useful. All right. In summary, in our work, we described how to utilize this the illumination design and then the end-to-end optimization of this in this differentiable camera regime to achieve the superhuman capability for the specifically in our work for depth imaging, right? And we believe that jointly optimizing our illumination design and camera system and our reconstruction algorithm will going to allow us to open up the new potential of this computational imaging. Yeah, thank you very much. That was my session about differential illumination and camera. Thank you.
With this, we conclude our course on differentiable cameras and displays. I hope you are now familiar with the range of concepts spanning displays, cameras, and illumination. The course material and our contacts are posted on the course website, which you can find in the bottom right corner here. Feel free to reach out to us for questions and collaborations.